Okay, so today we will start with the next chapter, which is all about, estimating the distribution function for the lifetime of the individuals that we will observe under a study that we are trying to do. Okay, so even before we start off with that lecture, I want you all to recall this particular example that we studied in the very beginning of our lectures. Does anyone remember what was the issue with this particular study? Anyone? No one? Can you guys hear me? So none of you remembers what was the issue with this particular study? Okay, let me just spot some particular things here. So the thing that we were trying to study here is what is the average age of people born in these particular years when they die and they're buried in a particular cemetery, which is Princeton Cemetery. So the issue was that after a particular point in time, we saw a decrease in the average age of death of people. So does anyone remember what did we think about this particular graph and what did we conclude? Or just, what was the issue with this graph? Is the average age of death or the age of death declining throughout these years, let's say after World War I or something? Or was there some issue that particularly made result, appear in such a manner, such a graph? Come on, I think it should.
I think, ma'am, we have collected this data before 1980. That's why we don't know. We have a declining graph there. Like, means the people haven't died yet, but they are of that age.
Exactly right. So very good, Meher. Thank you very much. So we saw that, let's say this study was done from, so we observed, let's say, people from 1720 till 1980. So we know for sure that people born in 1720 have had the privilege of being able to live for 100 years or more than that as well, right? Up until 1980. So we know for sure that we can observe people dying who were born in 1720 at the age of 60, at the age of 70, at the age of 80, and so on. But for the people who were born in 1900, they haven't yet achieved the age of 83 or 84. So we can never know if those people will be dying soon or not. And as in when we move closer and closer to the end of the study period, we see that the age of death is declining. But this was just an illusion, right? Because none of these people who were born in these particular years have yet until achieved these ages. So there is no way possible we can observe any observation for these ages at which people born in those particular years could die. So this is something, so the thing that has happened here is, let me maybe just draw something here. Okay, so let us say I'm starting here, and let us say I've started observing lives here, and this is the end of my study period. So what I did was I saw whether a person died at this age, or died at this age, or never died at all. Or so this particular here represents the starting point. This represents the time when a particular person was born. So if I'm looking at these things, and this is my 1720 and this is my 1980. So now if I'm trying to measure the duration of death, which is precisely what you mean when you say age at death, right? Because that is the duration from this particular till this particular time period. So let us say you have had one person, then you have had some another person, then you have had some one person, let's say, who died here, and another person who, let's say, died over there. So what you will do as a researcher, you ignore this. You ignore this because there is no death observed on these two particular lives. But there was a death observed here and there was a death observed here. So there was a death observed here and there was a death observed over there. So now once you exclude these lives where there was no death observed, because again you want to look at death of people. So you are trying to in a way bias your data set, because now what's happening is you ignore the fact that these people have neither died up until this age, or they have not died up until this age. So whenever you're trying to model, let's say, even for the people who might have drawn this graph, they had some data set like this. So what they did was they ignored these lives and they only took into consideration the lives for which they observed a death, which was the thing that we were trying to model this particular thing for, right? We wanted to know people's age at which they died. So this person did not die, this person did not die. So we didn't take those lives into consideration. So what happened was, by doing that, we have foregone a very crucial part of our data set. So not every time this kind of analysis will give you some logical conclusion. So you see here, there was no logic, at least not the logic which these people might have explained in the paper. So again, these kind of mishaps can be prevented if we try to also take into account these particular lives. Okay, so now if we say that now I want to take those lives into account, again there's the question mark, right? Because so I haven't observed death for these people. So what do I do for these people? Because there's no way that I can take that into account, because what I care about is the age at which these people die, and these people haven't died at all. So where do I include them in my analysis? And that is where today's chapter comes into the picture. So in statistics, they have created a separate branch of survival analysis. Why? Because in survival analysis, we often have to deal with, data which might require some sort of censoring. And when I say censoring, I mean data like this. So data points like these two are censored to the right. So we'll, in short, we'll study what censoring to the right means. But yeah, what we will now try to do is, we will not ignore the data for which we haven't observed our event happening. We will try to take those into account, and we will claim something else, and we'll call it censoring for, let's say, some lives that do not die. And again, the next issue that might happen if you're working with a similar data set is, let's say you started observing one particular person who was born here. You observed them, but then that guy vanished. That guy never, you couldn't locate that particular guy thereafter. So you never know if that person is alive or dead. So for these particular lives, we will do the same sort of thing. So we'll consider them as being censored. So we don't know much more beyond some particulars So we don't precisely know whether this person died or not, or if at all he died, when did he die? We have no information about that. So what we will try to do is we will try to just use the information that we have about that particular person to try to model as effectively the death data that we can. So here we were looking at the age of death, but now as we know, the thing that we are taking into consideration is not normally the age, right? We talk about the probability that a particular person will be observed to be dead after some amount of time. So again, before we do that, let us try to see what are reasons you might have for which you might have to censor your data set. So one that we have studied is, let's say, the individual doesn't die throughout the study period. So you know that we'll have to censor this particular individual at the end of the study time because this person did not die at all. So one, then second is again we saw in the pink one that we were not able to follow up with that particular person. So we don't have all of the data set regarding that particular observation. So we only have some data and we'll need to censor that data. So that is second. And third is sometimes we do not lose track of people. Sometimes people voluntarily, so they might just say, okay, now I do not want to be a part of this investigation anymore. So they might voluntarily withdraw from the particular study that they have enrolled for. So that could be one of the reasons we might have to censor the data. So again, whenever we're trying to censor, there can be various different kinds of censoring. So the first censoring that we saw was if, let's say, there is no death for some lives. So that kind of censoring is normally known as right censoring, where we know for sure that the survival time or the time to the event, and event being the death in this particular case, is greater than the end of this time period of study for us. So we know for sure that this particular person has not died up until this particular age. So, well, all we know is that the true lifetime of this particular person will always be greater than or equal to the observed survival time. So, when I'm talking about observed survival time, what I mean is the survival time that we observe a particular person for. So, let us say we start some study in 2014 and end our study in 2017, then we'll definitely see some people who do not die up until 2017 as well. So we will just know that these people haven't died up until 2017, but they might die later on. So we know for sure that their lifetime is greater than or equal to some value that we have specified. So that value will be the age that they have attained at or in the year 2017. So that will be something, that will be one of the examples of right censoring. So you might guess, so why do we call it right? Because we're trying to censor it in the right. So the thing that we saw was something like this. So let us say if people die here, and then this guy doesn't die at all. So you're censoring it from the right. And that is why this is right censoring. So again, I mean, so there can be two particular cases where you can have right censoring. Again, this is not exclusive. These are just example of two particular cases. So one will be that the observed life is alive till the end of the study, and second could be you lost follow up. So basically, you can't follow that particular person anymore. So that would be another example for right censoring. So again, in your books, they have given you much more, many more examples about right censoring pertaining to the insurance sector and specific to the actuarial nature. But again, this censoring concept is not only limited to actuaries. This is very heavily used actually in medical studies. So let's say if you're looking at some disease or something else, then these are very useful in analysis. So the second kind of censoring that you can have, let me just give you an example first. So let's say this and this is right censoring. Okay, so now maybe what we can take example of is the coronavirus, right? So you can actually have a coronavirus example for right censoring as well. We'll maybe see that later on. Yeah, so the first thing, let's say, I have a time 0 here, which I don't know. And again, I'm just representing time here. So what can happen is, let's say a person has been exposed to coronavirus, and then that person develops some symptoms, and then that person will, let's say कि चलो अभी test कराते हैं. So let's say if that person goes to a hospital and takes the test, then let's say that person goes to the hospital at time t, and the test comes out to be positive. So the test result is positive. So now what you know about this particular person is that at time period t, this particular person had coronavirus, and you can never be sure about when exactly that person caught the virus. So now what's happening is you have no idea when exactly that person got the virus, but you only know that at this point in time this person had virus and this person was tested positive with the virus. So these kind of censoring, so again this is something where you don't know some information to the left of the timeline that we are observing. So this kind of censoring is generally known as left censoring. So if you see here now what's happening is, you know for sure the duration that this person will be, let's say, positive with the virus, but you do not know for sure exactly when did this particular person caught the virus. So the exposure for the virus, you have no idea when that precisely happened. So again, in your books, they have given you much more examples, but I guess this is, if we do one particular example to see all kinds of censoring, I think that will be good for you guys to even develop some intuitive understanding. Okay, so now if you see, we have a right censoring, we have a left censoring. So the big question we have is, can we have both kinds of censoring at once? Maybe yes. So let's see. So if we have interval censoring, so what happens in this particular case? So right and left censoring are actually, a type of interval censoring. So these are two different types with different limits. So when I'm talking about interval censoring, let us just take the example of virus again. So let us say a particular person thinks that this person might have got the virus. So at time t1, they go and take a test, and the test comes out to be negative. And then again, this person goes and the test comes out to be positive. So now this particular scenario will be a situation where we'll have to take into consideration interval censoring. So we know that when we took a test at T2, this person was tested positive. But when we took a test at T1, this person was not tested positive. So what we know is that this person was negative up until this time. But again, we don't know when in particular this person caught the virus. So these particular kind of scenario will involve interval censoring, where you will observe both right censoring as well as a kind of left censoring. So I guess these are three main types of censoring that you observe. But again, there are many more types. So again, I think even before we study that, I think I should give you guys one example. So even the example that we saw, I think would classify as this, but I have one more example. So this is again, from some studies. So this is actually concluded by many studies in USA that, if you take the average age, okay, if you look at the mortality, if you look at the force of mortality for Latin American immigrants, that will turn out to be substantially lower than the mortality for the Native Americans. And many studies then, actually concluded this fact, and this was very surprising. So there was some more depth research done into it, and what turned out to be the fact was that with these immigrants, what happened was whenever these immigrants were, let's say, very old, or when they became terminally ill, or they were on the verge of dying, they used to go back to their home country. So they didn't stay in America anymore. And that kind of rendered this whole illusion of the force of mortality being lower for the immigrants than the native ones. So again, what's happening here is that the kind of people who are leaving the study in between has affected the random variables of the observation period. So sometimes you have to take into consideration whether the people who are leaving the study affects the rest of the people who are in the study. So is there a particular reason dependent on the fact that we are trying to consider that people are, leaving this particular study? So this shouldn't affect the, for example, the force of mortality that we might be trying to figure out. So when this is not the case, when people who are leaving leave at random, that kind of censoring is known as random censoring. So again, now when I'm talking about random censoring, this is a censoring. So this is a specific type of right censoring, because what happens here is that people leave the observation. You don't observe them anymore. So again, in random censoring, the thing that we care about is that the censoring time, the time at which people leave and the way people leave, is not at all dependent on, let's say, them being dead, or them being dead, which will be used to figure out the mortality rate in a way. So here we just try to consider that, the people who are being censored and the people who live up to their lifetime do not have any connection. And the people who live up to their lifetime are the people, again, whom we observe. And by lifetime, I mean the lifetime of the observation period that we have taken into consideration. Okay. So now what happens is, again, for the particular life that left the observation, that left the study in between, we will never know their actual lifespan. So if I denote my T, again, being consistent with the previous chapters, if I denote my T as the future lifetime of this particular individual, which I denote as I know that either this Ti will be observed. So either I know the actual lifetime of this particular person, or that person will be censored. So Ci, I'm denoting Ci. So again, these random variables denote time, and this Ci will denote the time at which the observation got censored. So time at which the ith observation got censored. So now only the smallest of these two numbers you will know. You cannot know the censor time if you know the TI, because then then the life has not at all been censored, right? Because if you know the TI, then you know the actual age at which this particular person died. So then this life was not being censored, right? Because the event that is being observed for this particular life. So the thing that we will consider is Ci being less than Ti. So again, Ti is something that we will not observe. So if this is the case, then we know that Ti is not observed. Because if my censoring time is lesser than the actual survival time of this particular life, I know only the information up until this life got censored. After that, I have no idea. So the only thing I know about this particular life is that Ti is greater than Ci. That's all you can know. So Again, these are just two denotations that I'm going to use. So again, here in case of random censoring, this is what we have. But again, some other times, what might also happen is you can define censoring in your study. So sometimes, let us say, in the previous chapter as well, we saw some examples, right? Where we were trying to study people only between the ages 70 and 71. So let's say if a person attains the age of 71 in the middle of the study, I mean, if I mean you can just say that we'll try to have people who were born precisely today, uh, who were born precisely at some time, which makes them aged 70 today. So that is very unlikely to happen, and to and for you to find those sort of people again, you will not have. I mean, that will just incur a lot of cost. So what you do is you try to take into random number of people who are much more likely to be in the ages 70 and 71 during the time period of your study and your observation. So for some people amongst those, you might see that they have attained the age of 71 in between of the study. So what you will do is you will have them censored. And now what happened was your study already specified that this particular lives will be censored at their being aged 71. So now what happens is you already know when a particular life is going to get censored even before you started the study, right? Because the time you admit these people into your study, you know their age, and you will know when this particular person is going to become 71-year-old. So if that kind of censoring happens, then it is called type 1 censoring, where the censoring is deterministic. So you know a priori when your objects are going to be censored or when your subjects are going to be censored. So here you already know CI in advance. And again, this is, I mean, if again the censoring is random, then this would classify as some sort of a type of random censoring, a special type of random censoring. Okay, so again, whenever I was talking about random censoring, there's actually another name given to this particular kind of censoring, also non-informative censoring. So whenever I say non-informative, what I mean is that these particular people being censored provides me with no additional information about the lives who didn't get censored or who were continued in the study. That is why these are non-informative censoring. And if it affects, which was the kind of case in our Native Americans and the immigrants study, those will be, I mean, that kind of censoring will be informative censoring, because a particular specific type and a particular nature of people is dictating the censoring that is happening in the study. So if that happens, then it's example for informative censoring. Okay, so sometimes if you know already, you know, when these particular lives are going to be censored, that will be classified as a type 1 censoring. And you know that this is generally observed in actuaries. And again, in actuarial domain, we usually observe. Okay. Yeah, so we usually observe right censoring in actuaries. So again, but there is another kind of censoring that might also happen. So that will be known as type 2 censoring. Okay, so the example I can think of right now is, well, let's say if we are trying the vaccination trials. So the vaccination trials for coronavirus are going on these days. And what you do is you decide a particular number of people to cap at. So let us say if you're trying some vaccination and you want to see the side effects, and let's say if you think that one of the side effects of this particular vaccine could be that, you know, I mean, what happens in a vaccination is the same bacteria you try to infuse in the body. So this particular person might develop a serious case of a coronavirus further on after the vaccination. So let us say if we assume that if that happens to 20 people, 20 is I guess a bit more number, but I have no idea of what is a bigger and what is lesser number. So let's just keep it at 10. So if a serious case of coronavirus develops in at least 10 people, then we will stop the trials for that particular vaccination, right? Because people's lives are at risk here. And what we have now censored, so in a way, we haven't said that we are looking at people from ages 70 to 71, no. We haven't said that we are looking at some particular time, no. What we said is, if 10 people get more sick with the vaccine, then we will stop the trials. So if this kind of censoring happens, then that will be known as type 2 censoring. So again, coming back to what we are trying to see, which is mortality rate. So we'll look at the death of people. So if we have some particular number of deaths observed, so some particular number of deaths observed, you stop the trial. And if you do that kind of strategy, then that will be known as, basically type 2 censoring. So the people you will not observe anymore. And yeah, so these kind of censorings are actually much more widely applicable in medical studies, as you might have guessed, with the vaccines, with the research that might be going on, with the symptoms that patients might develop. So you might have some cap. Let's say if these many number of patients develop serious symptoms, then you will stop the trials, or you will stop the particular drug dosage or something else, I guess. So yeah, these are different examples of the kind of censoring that we can have within the data set that we are being provided to do some analysis upon. So again, now what we will do is there are so many different ways in which we can try to analyze this particular data and come up with a mortality rate, which will help us again, answer the questions that we want to answer. So in majority, there are two types. One is parametric approach, where what you will do is you will assume that your mortality rate follows a specific functional form. So if you guys remember from the previous chapter, we studied compounds and Mechem. So in that, we assumed, right, that my mu is something BC raised to X. So we have already assumed a particular kind of function for the mortality rate. So if that is the case, then you classify it as a parametric approach. But the only thing left for a researcher to do now is figure out the parameters, and the model is being already decided. Only the parameters can vary. So what you have to do is just take the data, MLE, and figure out the parameters that will best fit the data that you have observed and the model that you believe is true. But there's another kind of technique that you can use, which goes by the name of non-parametric, so opposite. And here, as you might have already guessed, we do not use any specified functional form to try to figure out the mortality rates. So everything that will happen will be based on the kind of data set that we have, and we'll just, so first now we will study two different ways in which we can try to analyze the survival function and the hazard function. So survival function, as we all know, is, Sx of t if I'm considering in tx, and S of t if I'm considering the random variable t. And when I'm talking about hazard function is just a very general name. And the hazard that we are caring about in this particular chapter is the death of people. And that is why what we will want to figure out is the mortality rate. So let me just pull up the book, I guess, because there's so much. I mean, what I am planning to do is directly show you guys an example, and we'll see how to go about using these methods, using these examples. Okay, so the very first method that we will study is actually called the Kaplan-Meier model. And so it's actually funny, So Kaplan and Meier, these are again two different people. So This Kaplan guy was actually a classmate of John Nash, the game theory guy at Princeton with his during his PhD. So they both graduated actually at the same time. But again, when this Kaplan guy was writing his PhD thesis, his doctoral advisor was a guy named John. And what happened was, so just remember that his doctoral advisor was a guy named John. Even the other guy who is Meyer in this particular study, even his doctoral advisor was John, the same John. Okay, so now what happened was, these two, both of them together published a manuscript to a journal, and it was about the same thing. So, which is this particular model that we will now study. So what happened was, luckily, the journal editor for the same journal, which is, I guess, American Statistician Association, it is some name like that. So what happened was, the journal editor was these guys' doctoral advisor, John. So what he said, he made these two guys agree to write a combined paper and then submit. And then this is the model that turned out. So yeah, this is a very, very heavily cited paper actually, because this technique is much more used actually, in fact, in medical sciences than in actuaries as well. So we're going to skip the theory. Yeah, and we'll directly look at the examples. Yeah. So the question, so again, I mean, we have rats and we have a lab, so you can guess what's happening. So suppose that a group of 15 laboratory rats are injected with a new drug and they're observed over the next 30 days. So first thing, the number of rats we are trying to observe is 15. And the number of days we are trying to observe them over is the next 30 days. So let's say a month. Okay, and now these are the events that have occurred during these particular days when we were observing the rats. Okay, so here again we have labeled rats. Rat 1 represents rat 1 and so on. Okay, so here what they're trying to say is that on day 3, rat 4 died from the effect of some drug. Then, okay, so remember the thing that we want to care about is what happens when you inject a new drug into these particular rats. So this is the event. Whatever happens due to the effect of drug, so if a particular rat dies due to the drug, then that we will classify as an event. But if something else happens, if a rat bites the other rats and that rat dies, that is not an event for us. So that rat dying is something like that rat being censored. Okay, so here they have given us some information. So again, I'm going to do this simultaneously. So we are going to draw a timeline with respective times that they have given us here. So you just write those, and then if you see here, rat 4 dies from the effect of a drug. So if there is a death, you write it here. Then at day 4, rat 13 dies. So again, this. So here a rat blah 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 and escapes. So this rat 7 has escaped the lab. So now we don't know if this rat had died or what happened to this particular rat due to the drug. So the thing that we write here is C for censored. So when I write C, I mean that this particular rat was being censored. So again, I'm not writing the number here. I mean the number for the rat. I'm writing my times here on the x-axis. So what I have in the lower here is time here. Okay, so now if I look at 11th day, what happened was rat 6 and 9 die from the effects of drug. Okay, so we never said that, no two rats can die at the same time. So yeah, here at time 11, 2 rats die at the same day. So then rat 1 killed by other rats. So again, this is just censoring. Rat 10 dies from the effect of drug. B. Rat 8 freed during raid. Wow, this can be tongue twister. Whatever. So free, oh yeah, so we have a censoring here. And now rat 12 accidentally freed. So again, a censoring here. Then this guy dies from the drug. So D here. And here the investigation closes. So now what's happening is, this is the kind of thing that we studied previously, right? Right censoring. So here, so all the rats that do not die or do not escape, so basically to just, be exhaustive, all the rats that do not die or do not get censored at the end of the study anyways. So here, if I'm looking at the last day of my study, I can just tell that the remaining 5 rats, I have censored them now. So I'm not observing them after this, beyond this. So again, here, this is again just one example of right censoring. So here, these were the events given to you, and this is the timeline that you have drawn. So now what we will try to do is, we will try to use this particular data that we are given to figure out the survival time for rats, or the mortality rate for rats, or anything else that we might want to answer. So, okay, now what we will do is, again, I haven't shown you guys the notations that we'll be using. So we'll directly see it through this example. Okay, so I define small n as the number of lives under investigation. So again, we know we observe 15 rats. So we started observing 15 rats, and that is why my small n equals to 15. And then my small m will represent the number of deaths that happen due to the drug related issues. So we can count here 1, 2, 3, 4, 5, and 6. So m is equal to 6 here. And then the number of times at which deaths were observed. So this is important because we remember that at the day 11, 2 rats died at the same time, at the same day. So the number of times that we have observed any rats being dead at is 1, 2, 3, 4, and 5. And that you denote by K. So here your K is just equal to 5. And then what you do is you define new times. So now you define this T1, T2, T3, T4, T5. So again, these T's can only go up until K. And T1 will be 3, T2 will be 4. So now if you see, these are not, equally spaced intervals. But the thing that is common here is that between 0 and 3, there is no death. Between 3 and 4, there is no death. Between 4 and 11, there is no death. So now what we are trying to do in a way is, because it will be difficult for us to see what happens if we have, 1 death in some interval, 2 deaths in some other interval, what we do is we redefine our time intervals. And the way we do it is that in no time interval, we observe any particular death, right? So death happens at 3, 4, and so on. So whenever we're looking at the duration in between a particular time interval, the number of lives we expect to be dead should be 0. So I hope that is clear. And now what we are trying to do is number of deaths observed at each failure time. So remember, all of these times that we have defined represent a failure time. So by failure, they mean whenever we observed a particular death. So that time, so again, T1, D1. So these will be, so the number of deaths you have in D1 will be corresponding to the number of deaths you observed at time T1. And then here T2, D2, and so on and so forth. So here if you see T3, which corresponds to T11, is 2 in number, because 2 rats died at time 11. So I guess, and that you denote by D1, D2. So now if you add up all of these Ds, you expect to get this M, right? Because this is the number of deaths observed at each failure time. And if you sum them up, you get the 6 here. And then now what you do is you also care about the number of lives that didn't die because of the drug. So in all, that will just be N minus the number of lives that died because of the drug. So 15 minus 6, and you get a 9 here. But now, out of those 9 lives which did not die because of the drug, we know some of those lives got censored. So now when I'm talking about censoring, I will not look at the actual time here, the time interval is what I will consider. So again, I will redefine, I'll use my redefined time intervals, and I will define how many number of lives were censored corresponding to each of these time intervals. Now, one question you might ask me is, let's say at 21, a rat died and a rat escaped. So if both of these things happen simultaneously, then what time interval should I consider that censoring in? So we make an assumption for this particular case that at least in this particular actuarial subject that we are studying, we are making an assumption that whenever I observe a censoring and a death at the same time, I assume that death happened first and then the censoring. So every time you will observe censoring sometime after the death. So that is what you assume. So you get C0. So again, if you look at C0, you see there is no censoring happening here. C1 is again 0. But C2, which is from let's say 4 to 11, you see one life getting censored. So for C2, you have 1. For C3, again, you have 1. And then you will have 2, and then you have all the lives getting censored, which is 5 here. And this is what you have. So you have got the data about censored, you have got the data about lives being dead due to the drug. And now what you calculate at the end is the number of lives alive and at risk at time. So at each particular redefined time intervals, we want to see how many lives we have at risk during these particular times. So now what you will have to do is just basically count the number of lives you have. So if you look at from 0 to 3, you have all the lives that you started off with. And this is always going to be the case, because the way we are defining time intervals is the very first time interval starts, here. So this is, let's say, the very first interval, and then the second interval will always start from the time you observe a particular death. So for every time, your N1 will be equal to your N. So this is 15. And then for N2, you saw that one particular rat got dead. So this guy was dead, so you have 14. Then if you see again, one rat died. So, wait, what? Just give me a minute. N1, N2, N3. Okay, yeah. So if I'm talking about N1, I'm talking about this, and this interval. So when I'm talking about N3, which is my third interval here, I know that one life got censored here. So that is why you subtract one rat which got dead and one rat which got censored. So you get a 12 here, and then 9, and then at the end, at the very end, you have 6 rats. So I guess so. Okay. The very first thing that you have to remember is this is the number of lives which are at risk at these particular times. So when I'm talking about N1, I'm talking about intervals, third interval, fourth interval, fifth, and so on. So I guess this is basically the general information that you will have to figure out. And yeah, this is just, saying to you that the number of lives you censor is equal to the total number of lives you start off with minus the number of lives for which you observe death. And why is this the case? Because for rats to whom nothing happens, we consider them as being censored at the end. So again, these 5 rats are also getting count in the censoring here. So I guess this is clear. And now what you will do is I'm just going to skip through all of these for now. Yeah. And what we want to do is we want to create a particular table like this. So now if you guys remember, what is TJ? TJ is the times at which I observe deaths of rats, right? This is 3, 4, 11, 21, and 26. And now DJ is the number of rats dying, and J is the total number of rats I have being exposed at that point in time. So 15, 14, 12, 9, and 6. And now if you want to figure out the hazard rate, which I'm denoting as lambda j hat here, you can also assume that this is mu j hat or something. But again, just to be consistent, here we are trying to take that as lambda j hat. So as we have already seen, and we have already derived, that my mortality is denoted by nothing, I mean, in numerator, you will have the number of deaths that you observe in that particular time interval upon the number of lives that are being exposed to being dead at that particular point in time. So for these particular time intervals and these particular times, you will determine this lambda j hat. And that will be nothing but just bj upon nj. So 1 by 15. And here one rat died, which is why you have 1 upon 14, and then 2 upon 12, then 1 upon 9, and 1 upon 6. And that is the case. So again, if you see something here, you have a 1 here, and then a 1 here. So 1 plus 1, 2 here. And if you see this 15 minus 1 gives you 14. 14 minus 1 does not give you 13 here. So you have to take into consideration, if you are trying to figure out some patterns here, you also have to take into consideration the lives that get censored in between. So again, these might not correspond to the pattern that you might ever try to figure out here. But there is a nice pattern that goes on here. So what I'm trying to do here is, so if let's say this is my rate at which rats are dying, then 1 minus of that is the rate at which I expect these rats to be alive. So this will be the survival rate for these particular rats. And that is nothing but nj minus dj, which is the number of rats that survive upon nj. And these are the particular numbers that you get. And this column we will study later on. So these are just some numbers that we have now studied, and let us go back. Or maybe let me just, okay. So now what we have is the survival rates for each of these particular intervals. And what I'm doing now is, so, okay, this survival rate is for the individuals from 0 to 3. Sorry, this survival rate is for the individuals starting from 3, and this survival rate is for the individuals starting from 4, and this particular survival rate is for the individuals from 26 to 30, because 30 is what we cap at. So now if you look at these particular survival rates, these are for these particular intervals, which they have given here as well. So again, for 1, I mean, you obviously do not see any rat being dead from 0 to 3. So you expect all of the rats which are there to survive. So this is expected, and this will always be 1. And then you have the rest of these as it is. But again, if you see here, these particular rates are not precisely what you see here. These do not match, right? So there is something else that we need to do to determine the survival function. And what is that? So we have to take into account the fact that if I'm calculating the survival rate for someone in this interval, then I for sure know that this particular rat has been alive for this interval, and this particular rat has been alive for this interval as well. So there is something like conditional probability going on here. So the thing that you will have to do now is multiply this with this to get to this actual survival probability for this interval, because being able to survive in this interval assumes the fact that you have already survived this particular interval. And again, we assume that these are independent in nature, and that is why this will come as it is here. But this and this multiplied will give you this, and then this and this multiplied will give you this, this and this multiplied will give you this. Or what you can do is you can just multiply everything that comes up and above this particular time to get to the actual survival probability for that particular time interval. So these are the numbers that you will get at the end. And then 1 minus of these particular values will give you the rate at which these rats are expected to be dead, which you denote as f out of t, again because we're looking at the estimator, because we have some data set. So these are estimates, and this is how you will figure out. And okay, so this in all denotes the survival function using the Kaplan-Meier estimate. And this Kaplan-Meier estimate is nothing but this particular thing that we did here. So let me just take you guys back. And now if you see here, this is precisely how you define the Kaplan-Meier estimate of the survival function. Any doubts so far? Yeah, so let me just see if I haven't missed anything. So here they are just, trying to define some relationships and so on. So yeah, here you see the summation of all the lives that get censored is this thing. And again here, yeah, so let me just walk you guys through this. So now whatever I'm going to say here, you guys will be able to relate back to the example that we saw. So if you see here, back in the example, we had my value of k as 5. So C1, C2 until C5 I had. Okay. So if I'm observing deaths in those particular time intervals, I denote them as D1, D2 till DK. And now when I'm talking about lives being censored, instead of giving them the subscript 0, 1, and so on, what I do is I define these lives getting censored as, so again, I mean, these lives do get censored between the times 0 and k, which is how we have redefined our time intervals. But now what we do is, for whatever happens after this k, so we just say that my tk plus 1 is infinity. So let us say if these are my 1, 2, 3, 4, 5, I don't plot some other time here, but I just say that this is infinity and this is 0. Why? Because sometimes if you have to subtract some things, so you will be able to consider a time here which denotes tk plus 1 to subtract this thing from, and you will be able to consider some time here which you denote as t0, and again that will always start at 0. So if you are looking at the age of people's death, which might be the duration that you're looking at, so in that case you will say that, okay, none of these guys are dying at the age of 3, so why should my t0 be 0? But then if you consider in the age of death, so let's say you can consider in the duration for which you're observing this particular people, then the duration will start at 0. So again, you have those. So, but again, that will just change the way you then calculate the age at which these people die. So you just have to add up the age up until which each of these people survive, or at least the ones that you're observing survive. Then they have just given some assumptions that we need to assume. Okay. And then we saw this example. All right. So now here, if you see, what happens is within each interval, there is no death that we observe. So we assume that the hazard rate, the mortality rate in this particular scenario, which is the hazard that we're talking about, remains constant. So that is the case that they're considering here. And if that is the case, we know the survival function, which is like sxt, which is nothing but tpx, is just e raised to minus mu of t. So once, I mean, this is just something that you need to know. And again, I will explain you what do they mean by piecewise exponential within each interval. I'll tell you soon what that means. But yeah, and this we have already seen the hazard. It is dj upon nj, where dj is 0 for all the cases wherein someone does not die, or if they get censored or something else. Okay, so now we kind of assumed that we already knew this, but you can also derive this, and they have shown you the derivation, which I'm just going to walk you quickly through. Okay, so what we are doing here is we are just forget about this product for now. We take into a life wherein lambda j is the probability that this particular life might die, and 1 minus lambda j is the probability that this particular life will survive. And dj will be 0 if this particular life does not die, and it will be 1 if this particular life dies. So that when I'm taking the product for all the time intervals that I observe this for. So if you see, this goes from 1 to k, not from 1 to the t that I was observing this whole, so not from 1 to 30, this will go from 1 to 5. Why? Because we have chopped our time intervals and we have only defined 5 different time intervals. So now for, each dj and each ng and each lambda j will be corresponding for each particular k that we have observed. So this lambda j, which is the rate at which rats might die, is being raised to the number of rats that you observe to be dead. So when I said that dj is 1 when a rat dies, I know that my dj will in all, if a total, will just be the number of rats I observe being dead. So that is how you define the function that you will have here, and then you apply a log and so on. So I guess, yeah, so they have done it here. So you will apply a log to this, and then you differentiate it with respect to lambda 1, equate it to 0, and you will arrive at this particular thing. So again, if you see here, we have different lambda j's. We have lambda j. So for the rat case that we studied, we'll have lambda 1, lambda 2, lambda 3, lambda 4, lambda 5. So we'll have 5 different lambdas. So what you do is you just assume one of these. So you take lambda 1, and now you do it for lambda 1. And because of the symmetry, this will come out to be true for each of these lambda j's that you observe. So again, you put a hat because this is the estimator. This is the estimate. Sorry, for the estimator, that will be a random variable. You will get tilde. But yeah, okay. So this was the case. This was just some derivation for the particular lambda. But again, you don't have to memorize all of this stuff. Okay. So now the next thing that we will try to do is, this is just one way to think about the Kaplan-Meier survival function. What you can also do is you can think of this in terms of discrete distributions. So now when I'm talking about discrete distributions, what I'm trying to do is I'm trying to look at what happens at a particular point in time. So previously when I was looking at intervals, I was looking at, continuous, because I'm looking at these intervals. But now I can also try to have a look at what happens at these particular times, which are again defined by the times when I observe some rats being dead. And over there, you will have to define your lambda j, which is again, the mortality rate for rats, as the probability for, the time at which you so what is my small tj here? My small tj comes from here. And again, this you will observe for each of these particular intervals that you have created. So j will take values from 1 to k. So 1, 2, 3, 4, 5 will be the values. But again, here we are not looking at intervals. So if you see, we have a symbol equal to here. We are no longer looking at lambda j for between 0 and 3, between 3 and 4. We are looking at some particular time here. So that is what is happening here. And again, you do take into account the fact that this particular rats have to be alive for the previous time intervals. But again, I think maybe we should just have a look at this particular example here. So here, can you read this example, this question for us?
Yes, ma'am. Butterflies of a certain species have short lives. After hatching, each butterfly experiences a lifetime defined by the following probability distribution. Calculate lambda j for j running from 1 to 5 and sketch a graph of the discrete hazard function.
Okay, so what do you understand from this? What are we expected to do here? Anyone?
we have to calculate lambda for each time, like lambda.
Right. We just have to figure out our lambda for each of these times. Okay, so using the above formula, which let me just rewrite here. So the formula was that so the formula was that my lambda I is probability that t takes a particular value, which is tj, such that p is greater than or equal to tj. Yeah. So how do you guys think we can use this? So the information that we have is the days and the probability. So the number of days for which a particular butterfly will be. Okay, so who will tell me what are these days for? Are these the days for which these butterflies stay alive, or are these the days? I think it would be the same because they're just saying lifetime here. So it's given that these are the days for which butterflies will stay alive for. So now, how do you guys think we should go about calculating these lambda i's? So the hazard rate for each of these days, given the probability distribution. So 0.10 is the probability that the lifetime of a butterfly will be just for 1 day. So first of all, when I'm talking about this particular probability, just recall the fact that this Tj is the times at which we observe deaths. And this T here, capital T as usual represents, the whole lifetime. So here, if I'm talking about this particular I individual's lifetime being equal to this Tj, such that it is supposed to be greater than or equal to Tj. So when I'm pinning down that this T is greater than or equal to Tj, I know for sure that the lives that I'm observing at Tj, I'm not expecting any of those lives to be dead. So I know for sure that the T will be greater than or equal to Tj for sure. So I can again just rewrite this particular probability using the Bayesian formula. So what I will get here in the numerator is that my T is equal to Tj intersection, that my T is greater than or equal to Tj, right? Upon the probability that my T is greater than or equal to some Tj. So now if I go here, I know that my T being equal to Tj and T being greater than or equal to Tj, the intersection is just this. The probability that my T is equal to Tj, right? And the denominator will be as it is. The probability that my T is greater than or equal to Tj. So now I want you all to think how you will figure out this lambda j's for lambda 1. Let's just do it for lambda 1 first. What do you guys think I should write for lambda 1 as these particular probabilities? So let's say if I'm trying to figure out my lambda 1, what do you guys think I should write here?
I'm in the numerator, probability of T is equal to T1, so 0.1.
Yes.
On T greater than T1 can be written as 1 minus T less than T1, which is
yes.
So 1 minus 0 is 1.
Yeah, so maybe just let me write it nicely. So if I'm talking about lambda 1, what I should write here is the probability. Okay, so I guess this should be lambda j, guys. Okay, whatever j you have here is everything that you have there. Yeah, so this lambda 1. So what I'm talking about is t being equal to t1 upon the probability that t being greater than or equal to t1. So this can just be written as, so I know the probability that t will be t1. This is given to me. The lifetime will be just equal to t1, which I've defined as 1. So this is nothing but 0.1. But upon this, I don't know. So I can just rewrite this thing as probability that t will be less than t1. And now, as we know that all of these lies, I mean, there's no way this is going to happen. So this is just 0. So what you have is 0.1 upon 1. Because t being less than t1 has a probability of 0. So for everything that you don't have here, the probability is just 0. So this lambda 1, as we know, is now just 0.1. Let us try to figure out lambda 2 now. Savri, can you help me to figure out lambda 2?
Yes, ma'am. It will be 0.3 upon 0.9.
Okay, and why do you think it should be 0.9 in the denominator?
Ma'am, because it will be 1 minus probability of t is less than equal to less than t2. So it will be probability 1 minus probability t is equal to t1. So it will be 1
Exactly right, which is just 0.1. Very good. So Isha, can you tell me how should I figure out my lambda 3?
Hello, am I
Yes.
audible?
Yeah.
Yeah, so ma'am, for that we will just take 0.25 as the numerator and 1 minus 1 minus 0.4 as the denominator, right?
Yeah. So basically we'll just subtract everything that has happened before. So this is just going to be 0.25 upon 0.6. All right. And so on and so forth. So you'll just figure out these particular stuff for each of these that you observe. And now if you have a look at this, they've done the similar thing. And the way you plot a discrete function is just this. So for 1, 2, 3, 4, and 5, you will plot these respective hazard rates that you get. So the probability that you will observe some particular butterfly to be dead at day 1 is 0.1, and so on and so forth. So you see all of the butterflies will be dead by day 5, and that confirms what you started off with. Does this make sense? Any doubts so far? Okay, so now coming back to this, yeah, so now whenever I'm talking about the survival rates, I know it is S of t, but now when I'm talking about f of t, this represents the hazard rate. So when I'm talking about 1 minus f of t, this again represents the survival thing. So S of t, 1 minus f of t is same. All right, and now as we know, so 1 minus lambda j, and you just do a product. And now that is another reason why this estimate is also known as sometimes product limit estimate. So product, you know, because you're taking a product here, but why limit? So limit because we create these intervals, right? We divide the actual time of observation into some shorter time intervals, and we expect the mesh of these particular partitions to tend to 0, and which is why you have this particular limit here. So which is not seen here, but yeah, it's implied. So this sometimes is also known as product limit estimate. So if you see estimate written here at the end. So this gives you some idea that on this survival function, so this particular number that you will get here for this particular survival function is going to be a point estimate. So this is in a way a point estimate. And again, if you see this S hat of t is again defined for, all tj's being less than or equal to t. And if this particular thing exceeds the, so let's say if you have something like, tj being greater than t, then S hat of t will always be 1, because because of the way we have defined tj basically. So again, the product of empty subsets So the thing I was trying to say is that if you do a product over the empty subsets, you will get 1. But again, I mean, that is just some additional information and you did not know that. But again, that is just for your... Okay, yeah. So here they have used a word truncation and yeah, so here they're talking about data being truncated. Has any of you studied truncation before? Do you guys know what truncation is? Anyone? No? So, okay, in truncation also what happens is you do not observe the full lifetime of the person that you wanted to observe for the study. But here, whenever you are trying to do truncation, it is again based on the time. But now what happens is you exclude the whole observations. So in censoring, what you're doing is the observations that you censor, you include them in your analysis. But in truncation, you do not include them. So again, truncation can be left and it can be right as well. So, I mean, for example, let's say an example of truncation could be, let's say if you're trying to study the vaccinations effectiveness, then in your study, you will only take into consideration those people who have already caught the virus, right? Who are already, who are already sick. So this in a way is a fact that you're truncating your lives that you're trying to study. So again, I mean, they have used that data is getting truncated, but to, I mean, just to be strict and I mean, strictly, you do not, I mean, I don't think it makes sense to say that, you know, data is getting truncated. Rather, I think it makes sense if you say that the whole data set that we have is getting truncated. Because in truncation, I mean, you do not, you do not include the observations. So in censoring, you do include the observations. So you can say that the data is censored. But in truncation, I think it makes much more sense to say that the whole data set is a truncated data set. So we have only admitted the people who already have the virus. So something like that. So again, you might have truncation and censoring at the same time sometimes. But yeah, that is just, I mean, it does not in any way affect the way you try to figure out these particular estimates. And now that we're talking about this Kaplan-Meier estimate, again, this is a point estimate. So we will have a look at how to figure out this variance and so as to just be able to provide a confidence interval, not a point estimate, which might be 100% right or 100% wrong. Okay, so now again, the other thing that you can use, so basically, so what we did now was we drafted this whole table and we used this formula to figure out the survival function. But there's another approach that you can do. And again, you might kind of say that table approach is much easier. But once you get used to what happens in this particular model, you will see that graphical approach is way much more easier and it's basically just not tedious at all. So in table, you have to basically write the whole table and stuff. But in general here, you won't have to do all of that stuff. You will rather have to create a graph. And again, now you see why previously they said that survival function is a piecewise function. So if you see here, we see that this is a continuous function. I mean, if, and it's much more clear if I basically draw these lines here. Yeah, so you see that this is a continuous function, but again, this is not continuous as a whole. So the way we call these particular distributions is that it is piecewise continuous. Because for this particular interval, it is continuous, then continuous, then continuous. But again, there's something happening here. And now if I have a look at, so again, I'm looking at the same example from 0 to 3. I know that my survival function is 1. None of these is going to die. But at time 3, I observe someone being dead. So that is why And just to give you a perspective, the way we consider it is this. So at time 3, I will not consider this value. I will consider this value. And at time 4, I will consider this value. So that is why you see that this particular survival function is a right continuous function. And now you will understand why when now this is not working. Yeah, so now when we were trying to define this particular time intervals, you see there is a less than or equal to sign here, but there is no equal to here for 3. So we are not reaching 3. We are only looking at up until 3. And in this particular interval, we consider what is happening at 3. So that is one of the explanations. This right continuity property is one of the explanations of the interval being regarded in that way over there. So I guess this is how you will basically draw the graph. But again, you can't necessarily draw this graph until unless you figure out these survival functions. So the way to do that is, again, up until you observe any death, you know that this is just going to be 1. And now then you will see that there were 15 rats in the observation, and one of these rats die at precisely day 3. So for the next time interval, you will have your survival function as 15 minus 1 upon 15, which is just 14 upon 15. So 0.9333 for 3 to 4. So again, for this time, you have 0.9333 and so on. So for 4, it is going to change to what? So here, I think this is way much more evident. So now if you remember, you only have 14 rats alive. Then 1 rat dies. So now you have 13 rats being alive. So the hazard rate, the survival rate is what? 13 upon 14. But again, you have to take into consideration that this particular rat didn't die at the time 3 as well. So again, here you would ideally have this 1 as well, but doesn't make any difference. So you have 14 by 15 times 13 by 14, which will give you 13 upon 15. So you directly get the survival rate. So here, if you see, you do not have to figure out the hazard rate and then 1 minus and then the product of all of this. No, you directly get the answer for the survival rate. So sometimes if survival rate is the only thing you care about, then you can use this. But sometimes you might also want to figure some other things out apart from the survival function. Then you can look at, the table and you can figure out the hazard rate and everything else. So again, this is the same technique that you will do again and again to figure out the same survival function for this particular example, I guess. Any doubt in this? So now that we have, the estimates for our survival function for each of these time periods, now I can go on and think about its variance. So what I want to do is just, basically create a confidence interval for my survival rates that I have assumed. So again, you will have these for each of the times that you look at, which will be these. So again, this is not the only formula that you have for the variance, but again, this is one that is most commonly used, and this is called Greenwood's formula, and we don't have to care about its proof and all. So yeah, this is just how you will figure out so this is the formula basically that you have for figuring out the variance of this particular guy. So if you see here, we aren't calculating the variance of S. What we are calculating is the variance of F, which is the quite opposite of S. But the fact that my F is just equal to 1 minus S, and my variance of F will thus be just the variance of 1 minus F. So let me maybe write here, variance of 1 minus S. And this is nothing but, just the variance of S. So this minus will become squared, so 1 squared. Here you will have variance of 1, 0 and variance of minus S. This is just going to give you S because this constant can come out as 1 minus 1 square and so on. So basically you conclude that this is the variance not only for F but also for S. So you will use the same variance, and this is Yes, this is given on page number 33 of your table booklets. So this is good. And yeah, they've done the same thing. So I mean, it's important that we have to lay here to represent that these are estimators. If you put a hat and you write a variance, that is bullshit, because that hat represents the estimate. And you cannot figure out the variance for a particular value. That is always going to be a 0. So you have to remember that we can only figure out variance for a random variable. Thus, this S of t is an estimator, and for estimators, we put tilde here. So this is what you have. Okay, so now once you have this S of t, you will want to figure out the variance of this particular guy. And I think I'm not going to do that. But if you see this, they have just used the formula and they have just figured this stuff out. I think I can give you guys like 2 or 3 minutes to think if you understand this. And if not, I can tell you guys what's happening. But I guess this is fairly easy. You have DJs, you have NJs for each of these time intervals, and you'll have to just sum it up across for all of these. And this is just S hat 20, for which also you already know the value of. So again, I think the only question that might be here is, how do we know the value of this S hat of 20? Why? Because I mean, this particular S hat of t is true not only for 11, but for anything starting from 11 up until 21, not including 21. So 20 comes here in between, which is why you have 13 upon 18 here. And we were told to figure out the variance of S20, which is why you have this formula, and you're only looking at times where you have TJ less than or equal to 20, which is why you only have this 3 here, not all of these. So only 1, 2, and 3. You will not include these because you're looking at S20. And once you figure out the variance, you can again just, have the actual value, which will be 13 by 18 here, plus or minus 1.96, square root of this guy here. And that will give you a nice confidence interval. And again, I mean, these confidence intervals are based on the fact that we have large enough sample to assume that these MLE estimates are indeed correct. So yeah, this is a 95%, so 1.96. Any doubts so far? Okay, good. So now this was about the Kaplan-Meier estimate, and there is now another thing that we will study, another technique to essentially analyze the same stuff. But here what we will try to have a look at is not the survival rate, but the hazard rate. And again, by hazard rate, I mean hazard rate is what is used in general, and this is not only used in actuarial, in many other. So that is why this Nelson-Allen model is, it won't give you the value for survival rate directly, but what it will give you is the cumulative hazard function. And we'll see how that comes about to be. So there's a proof that they have given here, which I think maybe I can walk you guys through. So I don't know, it's quite odd that the name of this Allen guy is actually odd. So this guy's name is ODD, odd. That was just some fact that I wanted to mention. But I guess, yeah, all right. So here they have just rewritten this, so I can ignore this. That was Kaplan's formula. But now here, again, this is a non-parametric approach. We are not initially assuming or saying that this is the function that I expect my mortality rate or my hazard rate to follow. So we are not seeing any of that. Okay, so now here they say that this thing that they're denoting by capital lambda here just represents the cumulative hazard function. So when I'm talking about hazard function, I can say that that is, for so and so time intervals. But when I'm talking about cumulative, it means I'm summing it up across for every time less than or equal to some t that I can specify. So in the previous example that we just saw, that t was 20. So we added a bit all for the times less than or equal to 20. So here again, this capital lambda t represents just the same thing, which is cumulative hazard function. But now if you see that apart from this particular addition of all the lambda j's, I'm also having this integral here. So that is just to take into account the fact that sometimes you also have some part of the distribution which is continuous, and the other part of it is, let's say, discrete. So again, for the continuous cases, again, we know that P01 can be represented as e raised to minus from 0 to 1 mu of s ds. And for P02, okay, so this is again, so here, this is for the case of discrete, and this is for the case of, this is for the case of continuous, and this is for the case of discrete. So here, if my lambda is the hazard rate, then my probability that I will survive is just 1 minus the hazard rate. So here, you kind of assume that, half is, so again, this is the time half, but again, it just represents the probability that this particular life died at precisely, after 6 months. So like the average of 0 and 1. So 0 plus 1 by 2, a half. So we are assuming that this life is dying at the average, so in the middle of the interval that we are observing. So this is just an assumption. And now if you want to figure out, so again, if we assume that all of these is happening in one particular population and independently, then you will multiply these two, and what you get is something like this. But now again, if you see here, you have E something something, and this is very different. So now what you do is, this 1 minus lambda can actually be, so again, before you do that, what you will do is, this happened only for one particular year, and this happened, let's say, for 2 years. So, no, sorry, I guess this is for population 1 and this is for population 2. So this just denotes 1 P0, which is what's going to happen in the next year, but for population 1, which is continuous, and for population 2, which is discrete. So now if you do that in general way for till t, this is what you will get. So here you will have product of each of these, and here you will have e raised to minus 0 to t mu s ds. So now if you see, again, you can approximate e raised to x as 1 plus x. So here, if you have 1 minus lambda, you can easily, I don't know, I think you guys should already know this, but just in case, e raised to x, if it is 1 plus x, then I know that my e raised to minus x is nothing but 1 minus x. So here, if I have 1 minus lambda, this is nothing but e raised to minus lambda. And again, with the subscripts that I have. So this can be written as a product of e raised to minus of these things. And I know if I have product of multiple e's, I can write this as a e raised to summation of everything that is in the power. And that is what you do here. Because you have a minus, you get a minus here. And this is what you have for the survival function. And this is how you define your capital lambda t. But again, in general, what happens is this continuous part actually goes to 0. So what you're left with is just the summation of these lambda j's, which again you denote as, which again you will calculate as dj upon nj. So see a hat here denotes an estimate. So again, here we are trying to ignore what happens in the continuous case. But again, you do not have to remember that derivation and stuff. All you need to know is the function that you get for your survival. So this survival function is just e raised to minus capital lambda t, where capital lambda t is nothing but summation over all the lambda j's. And that is just nothing, dj upon nj. So this is something that you have. So if you remember in the Kaplan mirror, you would get a product, and over there you were figuring out the survival rate. So you had a product for 1 minus lambda j's. Here, what you have to remember is you're figuring out the hazard rate. And that is why you have a summation of the hazard rates. And then you know that this survival function is nothing but e raised to minus the hazard rate that you have. And again, the value of this hazard rate for something that doesn't satisfy this condition is just going to be 0. So that is how you try to figure out the hazard rate using the Nelson-Allen method. And maybe we should try to do that using the same example. So yeah, again, f hat of t here is nothing but 1 minus s hat of t, and you see this is the distribution function that you will get for the f that denotes the dying. All right, so again, this is the example that we just saw, and these are the estimates that you will get. So I think we don't necessarily have to do anything because previously we have already figured out DJs, we have already figured out the MJs for each of these intervals. So you just have to substitute in the values and get the answers for the hazard rate. Once you have those, you can estimate the survival function by e raised to minus each of these numbers. And this will be your survival function using the method Nelson-Allen. And again, this is how you will figure out the variance for the Nelson-Allen. And again, I mean, I'm not going to go through this again. You can see they have again done. So again, we are looking at less than or equal to 20, which is why 1, 2, 3 only. And this is the variance that you get. And you can figure out the confidence interval, 95%, using hat and the variance hat here. Any doubt so far? Anyone? All right. So again, I'm actually not going to write this thing again. Okay. So without me telling you, can you guys see some relationship between the Kaplan-Meier estimate and the Nelson-Allen estimate? Do you guys see if there is some relationship between these? Can you guys see? So the survival function for the Nelson guy is e raised to minus summation of all the hazards. And in the Kaplan-Meier, I have product of 1 minus hazards. So do you guys see some relationship here? So let's say if I tell you guys to, give me the value of Kaplan-Meier estimate that we have in terms of the capital lambda hat. So let me just show it to you guys because there's nothing new in this. So you can basically, so here we're talking about f hat, that is why you have 1 minus the product. And generally, if you're talking about S, that will just be the product and this stuff, no 1 minus stuff. So let us say, because I mean, they're looking at F here. So for the distribution function, wherein we are taking into account the events as death, we'll have this particular value for the Kaplan-Meier. And now if you want to rewrite this thing in terms of this capital lambda hat, so that you can build some relationship between this Kaplan-Meier and Nelson-Allen, then you would want to substitute instead of lambda, just dj upon nj. And now what you do is, again, they're just writing f hat of km to denote that this is the distribution function using Kaplan-Meier. And they will use NA to see that this is the distribution function using Nelson-Allen. And at the end, if you see, these are approximately equal to each other. So now what's happening here is you have just, you're just trying to represent again using this particular approximation. So here you have 1 minus this thing, and you just use this approximation to write this whole thing as e raised to minus summation of these stuff. And this is nothing but your capital lambda, which everything is nothing but f hat of Na. So remember, e raised to minus of lambda was my survival function, and 1 minus survival function is the distribution function. So these are actually equivalent to each other approximately. Any doubts so far? Okay. So again, this was how it's done. If we are not assuming a priori any particular function that our mortality rate or our hazard function might follow. So now the next thing is about the parametric estimation of the survival function. So here if you see we will assume a particular functional form. So again, they will give you example of Gompertz and the other stuff that we studied. So here if we assume a constant hazard rate throughout, then we know that the thing that we get here is the exponential distribution for the survival function. But again, that, to just include some variety and to make a distribution function a bit versatile, what we do is we add some scale and shape parameters here so that we indeed have the distribution which is viable, and the survival function looks a bit like e raised to minus alpha t raised to beta here. But again, now let us say we assume that my mu is following Compton's law, then you know that my mu x will be bc raised to x. So the only thing left for me to do now is basically just figure out these values for B and C here. So what you do is you use the MLE and you will figure out this particular values. But again, there is a trick involved here, just a little bit of something that you will have to be careful about, which is the likelihood function that you will have. Okay, so now we will have to actually see what is it that we are trying to consider. So, yeah, so okay, so now what we will have to do is we will have to write down the maximum likelihood function. And for that, we'll have to see what assumption do we put on these functional forms. So let us say the easier would be, the easy case would be if we have the exponential distribution, the mortality rate is just going to be constant. So I'm just going to go through with what they have in the books for now. So again, I'm just going to assume that we'll have exponential hazard function, which is why the parameter does not change and the parameter just stays one constant, which is mu. And we are considering only a single unit of age between exact ages x and x plus 1. Okay, so now again, you will have to meet certain practical issues where some people will die precisely between x and x plus 1. Some people might withdraw from the investigation, and some people might attain their x plus 1 per day within the times. All right. So what I'm considering here is the fact that these people might die even before I finish the observation. Not. So these people will attain their x plus 1 per day even before I finish my study of the observation. Yeah, but again now, if you see this particular consideration, where we actually observe death of a person between this and this age will be considered as the event. And these two will be considered as censored lives. So now when I'm trying to figure out the likelihood function, what you have to say is, what is the probability that this particular people will die and the probability that this particular people will be censored? And you will raise them to the respective numbers to get to your final answer. So now let us say we are looking at the life 1. So this particular life, let's say, dies at the duration t1. And as we know, we are already assuming exponential distribution. So my f of t when I say is mu e raised to minus mu t1. And now this is what I will have to maximize. So instead of maximizing, just it for the one life, if we observe k number of deaths, then you will have this thing as your probability density function for the lives that you observe to be dead. Again, remember, we are assuming that the distribution function that these lives have is exponential distribution. So that you have to always keep in mind. And again, this is just a product because again, we assume these lives to be independent of each other. And this product of deaths just means the number of deaths that you have observed will be the number of times you will take this as product. So here K represents the number of lives that are died, that are dead. And that is why you have this thing. So again, this particular function will not remain same now. Let's say now we assumed exponential, which is why this is what you get. But if we will have Weibull distribution, then this will not be the same. Because again, this f of t1 will be very different than what we have in this particular case. Okay, so I guess this is complete now. But now what will happen to the lives that got censored? Again, what we know for these lives that got censored is only the fact that they were alive up until they got censored, right? So again, let us say if we are looking at, death by some drug, and if a rat dies due to lightning or something, that will be considered as censored because the event is just the fact that the death happens due to the use of a drug. So if something else happens, and even if there's a death happening, but if that is not something that we are considering in nature, then that will be considered as being censored. Okay, that was just something that came, and I think I should let you guys know that. Okay, so again, now coming back to how do we figure out the function for the lives that get censored? Because the only thing that we know is that they were alive up until the time they got censored. So again, what we can rewrite here is only the probability that they survived up until some time. So now is the thing that, so now what I want to care about is the probability that some lives survived till some time. So now when I'm defining my time, I'm writing K as the number of deaths I have. So to ignore the overlap that you might have between deaths and being censored lives, what you do is you write here K plus 1. So now the thing that we will be looking at is Tk plus 1. So if you see here, we're looking at S of Tk plus 1. So this is nothing but this is actually taking into consideration all the information we know about the life that just got censored. So survival function for the exponential case, as we have already seen in the previous chapter, is e raised to minus mu t. And that is what you will have for each of the lives that get censored. And when I'm talking about censored lives and the dead lives, this will combinedly take into consideration all the lives that I'm trying to study. So again, all the lives that do not get censored in between the time duration and neither die will get censored at the end for sure. So this takes into account everything that we have. So this is the function that you will have for the censored lives. And now again, as we know that there is no dependency between the censored lives and the dependency and the lives that die and the lives that remain. So we are basically assuming that we are looking at non-informative censoring. So you multiply both of them together and this will be your likelihood function. So now you have this thing as your death and this thing for your censored, I guess. Yeah, for K plus 1, so censored, and from 1 to K, this is for the guys who won't die. So, and if you see censored one starts from K plus 1 and ends at N, because K is the number of rats who die, and then the remaining ones will be the number of rats which are getting censored. So this is what you will have as a final likelihood function. And now again, I think this is just the homework for you guys. You guys can do the same thing for the Weibull distribution and you will get some other likelihood function here. Okay, so now Actually, this likelihood function is still a bit, this is good in its nature, but maybe we can do something else to make it a bit more generalized. So now what you do is, instead of sitting and deriving everything, and generally what we observe is hazard rate, right? We know the value of the hazard rate. So we will try to see if I can redefine my likelihood function in terms of the hazard rate. So what I will do here is one simple addition. So you see, to obtain mu hat, I'm just defining some variable delta I, and that will take the value 1 if the life is dead and 0 if the life got censored. So you see, f of ti is raised to delta I to denote the lives that died and the probability that by which they are expected to be dead, and here the probability for getting censored, and here 1 minus delta I, so that you only have less random variables. Okay, but now again, if I'm talking about this f of t, this f of t represents the probability that some particular rat died at time t, right? And this can also be written as ppx times mu x plus t. So again, this x just represents, so if I'm talking about the age, this x will represent the age before my study started, and this t here represents the duration. So this t here, so this mu x plus t denotes the fact that this rat was aged at x plus t, and so on. So if you're talking about the people, yeah, this particular person died when that particular person was aged at x plus t. So you can, this tpx is again nothing but s of t, and I'm rewriting my mu, which is just the value of the hazard function here, which I denote as h of t. So that I can, instead of f of ti, I can rewrite this thing. So I'll have h of ti raised to delta I and s of ti raised to delta I again. But I again have s of ti raised to 1 minus delta I. So that will sum cancel, and you will be only left with s of ti here and h of ti raised to delta I. And for all we know, my hazard function is constant for the exponential case, and this mu will just be raised to delta I, and this is nothing but e raised to minus mu ti for s of ti in the case of exponential distribution, which is the functional form that we have assumed. If this were viable, you will get something else. So this is what you get here, and there is only one parameter. So you differentiate, you take logarithm, you differentiate with respect to mu, and you will get some particular value, which is this. So again, I'm not going to go through the whole derivation, but I think you guys can make sense of this. What is my mu hat? My mu hat is just k upon summation of ti's. So k is what? K is the number of deaths I observe, right? And what is ti? Ti is the risk, the total risk, right? So ti is the total risk that these particular rats have been exposed to. So I guess, the total time, if risk sounds a bit abstract, the total time these particular rats were exposed to being dead. So that is all you will have for the estimate of the mortality rate in the parametric case. So again, remember what we did? We assumed a functional form a priori, and then we just try to rewrite our hazard function and the survival function in terms of the parameters that we have chosen. And again, here we only have one parameter, which is mu. There's actually no parameter as such. And in viable, we'll have alpha and beta separately. So you'll have to take those into account as well, and you'll get some values. So here we get the value for mu, similar to what we actually saw in the very first time. The very first time we studied about this mu, remember we defined our small v as the exposure time. Then we started writing it as, expectation of VI and something of that sort. That we'll again see in later chapters. But now if you see, the summation of TI is actually equivalent to V, which used to denote the waiting time in our previous chapter. So that is what you will have here. And again, you only had one parameter here, so this was straightforward. But if you have more parameters, you will have to do the same thing again and again, and you will have to determine those values. So I guess Yeah, and then basically if you, you'll get some simultaneous equations and then you'll solve them together. So that's all. Okay, so I guess up until now, what we saw was if we assume that the age is between x and x plus 1, so that we have a constant rate of mortality, which is mu, that we assume is only for the case of, let's say, 1 year that we're looking at. But not every time this mu x will be same. So sometimes if I do not want to figure out sx1, but let's say I want to figure out sx4, then what will I do? So again, we just assume that these are independent. So you will multiply them together. So here you have sx1 getting multiplied by sx plus 1, 1. So here it denotes that the life has already attained the age x plus 1 and will not be dead within the next 1 year. So this is what we have. And again, this is mu x corresponding to this particular case and mu hat x plus 1 corresponding to this particular case. Because again, if these are equivalent, then that's even easier. But if we assume these are not equivalent, then you will have a different value for this guy and a different value for this guy. And now if we just try to do that for each of these cases, this is e raised to minus a minus b, you will get e raised to minus of a plus b in the bracket. And that is why in general, if you have to figure out this for m duration in future of x, which is nothing but mp hat of x, so remember hat here, this is nothing but expectation of, remember the minus here, the addition of everything from 0 to m minus 1 for this mu guys. So I think, yeah. So again, remember here, because we are starting from 0, you get a m minus 1 here. So that in all, you only have m number of terms in the power for the e guy here. And I think this is a very good example. So I guess let us just try to do this. This is fairly straightforward. So I'm being given the value of these mu's and we are being asked to figure out some values. So what will be the value of this guy here? If my mu hat of 60 is 0.01. Can you guys guess? What does this represent? This represents the survival function, right? So this will be S of 61, right? And I know that I can rewrite my survival function as e raised to minus mu t. And if my mu is being given to me, and if I also know my t, what will I have? So my t is just a 1 and my mu is 0.01. So this is going to be 0.01 times t. And that will be your value for P60. And now I want you all to try to figure out this particular value. This is actually, we have already studied this. So we can again split this as 1P60 times 1P61. And you can figure this thing out. Or you can try to use the formula that we studied here. So if you try to use this, what you will get for this particular guy is e raised to minus of 0.01 plus 0.02. And that will be your answer for this guy. And again, you will add up this here for this guy. Does this make sense? Any doubts? Anyone? So this is actually the end of chapter 7. And I think we'll see, okay, so Hetri actually told me that she's not going to take any